2, 1.
Hello and welcome again to our last talk here. And this one is a dense one. So, yeah, keep your and I would like to welcome Peter Hack. He's a solutions engineer at Harness, and he's here to talk about some very big buzzwords that we talked about today before as well. And yeah, I hope we're going to get loads of info in our last 15 minutes here on the track. And yes, take it away, Peter. I'm very excited to find out more.
Thanks a lot, Ava. So welcome to this talk. I'm going to be presenting to you machine learning and artificial intelligence for modern software delivery. I am a solution architect at Harness. And if you want to know a little bit more about me, well, basically, who the frick is Peter Hack? Well, I'm currently at Harness. I've had a few other jobs before that. I tend to find myself in high places in the cloud. I'm cloud native in that mindset. Or in very, uncomfortable situations, maybe even doing a talk about machine learning. And finally, well, that's not me, actually, that's my son, but a mini me taking risks, right? So this is an opportunity for us to kind of get into machine learning and understand how it's going to enhance our lives. When I talk about machine learning and AI enhancing lives, what I'm really aiming at here is removing the toil and the things that engineers just hate to do. It's not that it's going to replace jobs. It's just going to make it easier and better for the people who are doing those jobs. And think of it kind of like a rising tide raises all ships. In this case, better AI, better technology is going to just produce better opportunities to do other things, more valuable things. So, nobody likes to sit in deployments and war rooms when things go wrong. It's just a waste of time. It's an enormous waste of time. It's astronomically expensive. But there is free pizza, right? We get free pizza, so that's a good thing. Or we can minimize it. We can just do database toggles, things like that. But even though the changes are small, we still have to monitor them, and we have to be in those knocks for that to happen. And we get more free pizza. When we do our builds, when we do our testing, it takes an enormous amount of time and we have to wait. And there's better and intelligent ways to do this. But since that's the way we're doing it, we just take coffee breaks to make that happen. And finally, since this is cloud native, there's always a monthly cloud bill. And whether you are the one paying it or somebody else is coming to you to say, hey, why is the bill so high? These are things where AI and ML really can help solve a lot of these problems and make our lives better. So let's talk first about what software delivery is. It's pretty much a 101. Most of you are familiar with this at this point, but essentially we're building, we're testing, we're deploying code to our customer. The idea is to get code to our customer. Once we've deployed it, we verify it. We want to make sure that it's working well. And we use lots of different tools in all of these aspects of our business. And then when things go wrong, what do? We have to roll that back, and it can be an enormous amount of time. We could talk minutes, weeks, hours, days, months to achieve some of this. But when you have to roll back, when you have to fix a problem, you have to A, know about it, and B, you have to address it. And addressing it could take a lot of time. And that's really where automation comes into play, because if you have automation, then all of this can be done very, very quickly. But understanding verification to make that automation work is kind of a challenge, right? Today, we look at verification and we think of ourselves as like noise level monitoring. Is it up? Is it available? Do we see availability as a real benchmark for our application? Does the homepage work? Oh, I don't see any alerts. There's nothing in the logs. No one's complained. These are the traditional ways we do this. And that's really where the knock comes into play. Everybody's sitting there in a war room waiting for that deployment to happen. But there's a better way. It's through machine learning. Now, machine learning is not a silver bullet. It's better at most things or some things than humans. Let's just say it that way. But it doesn't solve all the problems. We're going to just kind of dive into this particular aspect of it. So when we look at machine learning, we're going to talk a little bit about things like unsupervised machine learning, letting the computer tell you what's going on. Is there a problem? Does it identify that there's something that it sees is wrong? It can look at natural processing, natural language processing. You can look at neural nets that have been built on models that have been created, but ultimately utilizing the power of technology to solve some of these problems to keep you from having to do that work. We also will talk a little bit about supervised machine learning. Really, this is where we're taking algorithms that require human assistance, right? We're providing feedback into this, right? Is this good? Is this bad? Should we ignore this? And ultimately through machine learning, right? The learning part is that it'll learn from our input, and that input will ultimately make it smarter over time. But what we're not talking about, and what actually becomes a big challenge, is that a lot of people talk about things like thresholds or SLOs and SLIs, and those are what we're going to measure against. And those are arbitrary numbers that are created. And ultimately, using things like regex or thresholds or configuration or standard deviation, well, that's just math. That's not AI. That's not machine learning. It's just math. And we want to get beyond that. We want to actually utilize the technology and the machine learning to help us do better. So how do we do this? Well, it's about context. When we think about context, what we're looking at is the application itself, right? The artifacts, the infrastructure, the deployments that we're doing, all the eventing that's coming in, and we're measuring that in some way, or having the system measure that against between control data and test data. Now, control data is what we're kind of going against. The control data is what we know, and the test data is all the new information that's coming out. Well, this is easy when we're talking about something like maybe Canary. Now, Canary itself is quite difficult. Canary, where you submit a small subset or a microservice of your application out into the real world, into production, and then run traffic against it. And you can easily compare it to one-to-one. You compare the traffic and the results of what you are getting for your KPIs on that instance against what's currently running, because they're both running in live production traffic. But it gets a little more challenging when you do other things. Like, what about in QA? Well, your developers can create baselines and use those as your test baseline, and then you can compare against previous tests. And that works pretty well in a dev or production environment. In a dev or a QA environment. But when we start talking about production, well, that doesn't really work, because we don't know what that traffic is going to look like. And I can't necessarily test if I'm doing, for instance, a rollout deployment where I'm just replacing the configuration that I had before, or a blue-green where I deployed blue against my green. I don't have a green running right now. So I can't compare that data. I'm comparing it to a previous subset of that data. And to be honest with you, in production, time is different, right? 5 minutes before is not the same production traffic as I have today. Yesterday's traffic is not the same as today. Weekend versus weekdays, holidays, things like that. So you have to really use another type of model, predictive modeling, to be able to identify that. So when we want to do this kind of testing, it gets a little more complicated. And here's where I'm going to get kind of nerdy. Now, I only have 15 minutes to explain AI and ML to you. So this is going to go a little bit fast, but understand that I'm just giving you a subset of the types of modeling that can be used. So first, let's talk about something called symbolic aggregate approximation. This is taking the time series metrics you might have, breaking them up into segments that are of equal length, and identifying variations between your test data and your live data, your new data, your baseline data, against that time frame for those segments of time. Now, this is really helpful in identifying differences, maybe anomalies, but the reality is that this type of anomaly detection actually is very noisy, because it's not taking into account the gaps, the differences between time shift or things like that. So when you do SAX-based algorithms, you then might want to introduce something like a hidden Markov model. The hidden Markov models are great because hidden Markov models introduce things like probabilities. So now we can do some prediction. For instance, if it's raining outside, there's a high probability that I'll probably go shopping online or maybe clean my room versus going for a walk in the rain. Although I do like to walk in the rain, it kind of washes the bald spots up here. Any case, we use hidden Markov models to be able to identify gaps in data or hidden areas where we don't have anything that we can measure against. But as you notice in this double shift here, we have if we look at this against the previous view, you'll see that there's two peaks. And those peaks in this are now flattened out because we can see that there's a prediction that the peak can occur based on the data that I have. So this incomplete data, utilizing Markov models allows me to combine my SACS information with my Markov models to be able to find these differentiations and basically suppress noise. But when we look at things like logs, I can't really use those algorithms. And in fact, if we were to look at logs, there's a lot of data. And we want to do what your best engineers do, right? That's really what we're trying to solve, is what your best engineers are doing so they can do the things that they're better at elsewhere out in the world. And we can apply that knowledge to machine learning. So when we look at something like detecting anomalies in logs, the issue that you run into is just there's so much data. We're looking at thousands and thousands of lines. And don't get me wrong, your best engineers are going to be able to figure things out and find problems, but not in a timely manner. And that's really what matters. Doing CD, doing your deployments in software delivery, it's very important to be able to solve problems quickly and identify when those problems are occurring. So when we're looking at logs, we want to be able to identify those anomalies and those exceptions in the logs. Now there's challenges here, right? Doing automated verification, we can look and see, for instance, on the left, that we deployed code, and this actually was an authentication service at the time that we did this, and we saw all of our applications started showing exceptions. Basically everything broke because it's the authentication service which touches everything. So there's thousands of errors that are occurring in this. So we see those anomalies. That's something that's really important to know about very quickly. Whereas on the right, this is a typical deployment. Maybe it's one service that's been deployed that's not all that impactful, but it does have problems. So you can't just say, I see a lot of anomalies, I want to do something about it. You have to be able to say, based on the context of what you're deploying, that they're equally important. And these are the errors that you should be focusing on. So when we're using learning with context, we're going to introduce things like entropy, right? We're going to look overall at all of the information. And in this case, for instance, I have a lot of ones and a zero. The ones aren't interesting, but the zero is the difference. That's the thing that's really interesting. So I can use my entropy to say, these are the differences that I'm concerned about. Then I can cluster all those differences together. And k-means clustering is really useful in bringing the disparate pieces of information that I classify as different together into different clusters of varying significance. But I have these clusters, and they're valuable, but they're all clustered, and I don't know any context about the actual differences. I only know that they're the similar differences. So now I want to use things like Jacquard distance to be able to break apart those distances and find the values that are, how far apart are they in those distances? Are they the same problem, but in a different part of the code? Are they different exceptions in a different part of the code? Or are they, for instance, the same exception in the same part of code? Like, all of these matter, and being able to figure out that distance of the application problem or exception to the classes that they reside in is a very important distinction. So taking that, breaking that apart from a Jacquard distance, now I have the differences, but I still need the distances of those differences, but I also need to figure out, well, are they important? Are they the same? Are they something that matters to me? And so now I have to figure out kind of basically pulling together those similarities of the distance, the differences in those distances of the different contexts that I found in k-means for my entropy. So all of these together are really complicated sounding, but you know what? You as a human do it like that every day. You classify things all the time, and their distances and their differences, and you can do this as a human instantly. The challenge and the reason you need to use machine learning for this is, remember, we're trying to teach machines to do what your best engineers are able to do instantly. However, on data sets that are infinitely large. far larger than a human can very easily do. So if we were to kind of jump through this a little bit, how do we break out that noise? Well, you got to use neural nets. Neural nets break apart the noise very easily. On the left, non-neural net, we have a lot of noise. On the right, we're able to break apart that noise. So building out these models help us break apart that noise. As a quick example here, I have a customer, they had a production failure. That production failure immediately was automated to understand that there was a problem. The product was able to identify those failures and point that out to the customer, but at the same time, roll it back in 30 seconds. Right? So this would normally have taken them 30 minutes. It only took them 30 seconds. This is the type of thing that ML and AI can help you when you're doing software delivery. I work for Harness. Harness is an intelligent software delivery platform, and we do AI and ML in all of our products. So this is something that really was just a subset of the delivery side. I'm more than happy to talk more about this in the future. And if you have any questions, please reach out to us. That'd be great. Ava, I see you have joined us. Thanks so much for the time here.
Thank you, Peter. Yeah, it's a complex topic and there's so much to say. I'm doing it in 15 minutes. I mean, great job.
Yeah.
You deserve a rest now.
Thank you.
Thank you so much for hanging out with us and for sharing all of that stuff. There was some math in there.
There was a little math. It's very mathy and nerdy. But yeah. This is normally a 1 hour talk. So
I can imagine that. So great job reducing it.
Thank you much.
Wonderful. And thank you so much for closing down this track with something so very interesting and also very important to all our fields. I mean, what you said in your last couple of slides with the customer reducing the time for the rollback, that's incredible. That's just, you can actually count that in money for many customers. So yeah, that's great. So thank you so much for your talk. And everybody, thank you for hanging out with us today. It was wonderful. Thank you all for your questions and for participating and for just simply being here. And I hope you had a lot of fun. This is not the end of the conference, though. This is just the end of this track. There will be more. And one of the many cool things is there will be a quiz on track 1. So please go to track 1 and participate in the quiz. You have a couple of minutes left, so don't worry, you don't need to run right away. You get a chance to win some stuff and test your knowledge on cloud native. So I think that's going to be fun. Then we will have a panel and some more chance for networking and more talks and more stuff. We are not done yet, even though it's dark outside. So yeah, I hope you had a wonderful conference so far, and I hope you had a lot of fun. And see you again in track 1. And yeah, everybody keep sharing our hashtag. Make sure that you are familiar with our code of conduct and visit our sponsors at their booths and also find people to talk to. So thank you very much, everybody. Have a good rest of the conference. Thank you, Peter, for hanging out with us and for sharing your knowledge. And
my pleasure.
See you later. Bye, everybody.